The universe is a grand, unfolding puzzle. Albert Einstein, a name synonymous with genius. He gifted us many crucial pieces, transforming our understanding of space, time, and gravity. Yet some connections he pondered remain elusive. He searched tirelessly for a unified vision, a single framework for all physical laws. Two of his most perplexing ideas stand out. These are often denoted by simple letters, ER and EPR. ER refers to Einstein-Rosen bridges or wormholes, theoretical tunnels, shortcuts through the cosmic fabric. EPR, on the other hand, describes quantum entanglement, a strange, almost telepathic link between particles. These concepts seemed worlds apart in Einstein's time, yet could a hidden thread bind them? Modern physics is now seriously exploring this startling idea, the notion that wormholes and entanglement are deeply connected. In 1935, Einstein, with Boris Podolsky and Nathan Rosen, published a paper that became famous as EPR. Its aim was to highlight what they saw as a flaw, a fundamental incompleteness in quantum mechanics. They devised a clever thought experiment to expose the inherent weirdness of the quantum world. Imagine two tiny quantum particles. Their properties become intimately intertwined, or entangled, linked, no matter how far apart they may travel. If you measure a property of one particle, say its spin, you instantly know the spin of its distant partner. This instantaneous, faster-than-light influence baffled Einstein. He famously and dismissively called it spooky action at a distance. Despite Einstein's considerable doubts and skepticism, countless experiments have now confirmed entanglement. It is undeniably a real feature of our universe. Quantum mechanics works, spookiness and all. The quantum world operates by different rules. Think of entangled particles as cosmic twins. Even if separated by vast interstellar gulfs, they share a secret, an unbreakable connection. What happens to one is instantly reflected in the other. An invisible, indivisible thread links their destinies. This profound bond defies our classical understanding of the world. It is a purely quantum mechanical phenomenon. Entanglement often begins when particles interact closely. They might be born from the same quantum event or brush past each other in a specific way. Then, they journey apart, perhaps across the laboratory or the cosmos, but they carry with them a shared quantum state, a kind of memory of their common origin. Despite the instantaneous correlation between entangled particles, entanglement does not allow for faster-than-light communication. The outcome of any single measurement on one particle is random. You only see the correlation when you compare results, which requires classical communication, limited by light speed. Quantum computers aim to harness entanglement to perform calculations far beyond classical machines. Quantum cryptography uses entanglement for secure communication. Now let us shift our focus dramatically, from the tiny realm of quantum particles to the vast expanse of Einstein's other great theory, general relativity, our modern description of gravity. In this theory, gravity is not a force, but rather the curvature of spacetime itself. It was within this framework of general relativity that Einstein, this time working with Nathan Rosen, explored peculiar solutions to his field equations. They discovered something truly extraordinary: the mathematical possibility of tunnels through spacetime. These were dubbed Einstein-Rosen bridges, shortcuts, potentially linking vastly distant regions of space. A wormhole is like a tube or a throat, connecting two different distant points on this sheet. It offers a direct path, a cosmic shortcut, allowing travel between these points much faster than traversing the distance across the surface. However, these theoretical tunnels came with problems. The initial models of wormholes were highly unstable. Science fiction writers instantly fell in love with wormholes. They became a staple for interstellar travel plots, pathways to distant stars, galaxies, or even other universes. Imagine stepping through a shimmering portal and emerging light years away in an instant. This powerful image captures our human imagination, our desire to explore the vast cosmic unknown. But what does the actual physics truly say? Most theoretical wormholes are non-traversable. They snap shut too quickly for anything to pass, or they are one-way trips into crushing singularities. To create a traversable wormhole, one you could journey through, physics suggests you would need that exotic matter, a substance with very unusual, repulsive gravitational properties to prop open the throat of the wormhole. Some early wormhole theories had intriguing connections. They linked a black hole to a hypothetical white hole. The search and the theoretical exploration continues. In 2013, came a truly bold proposal from theoretical physicists Juan Maldacena and Leonard Susskind. They put forward a radical, almost audacious idea. What if ER, Einstein-Rosen bridges, equals EPR, quantum entanglement? What if wormholes and entanglement are not separate phenomena but are, in fact, two descriptions of the very same thing? The core of the EPR conjecture suggests that when two quantum particles are entangled, they are, in a very real sense, connected by a tiny wormhole, a microscopic Einstein-Rosen bridge. This isn't a wormhole you could travel through, it's not a shortcut for spaceships across the galaxy, but it is proposed as a genuine geometric connection, a physical link existing in the fabric of spacetime. The seemingly instantaneous influence between entangled particles might not be traveling across vast distances in ordinary space, not faster than light in the conventional sense. Instead, the connection passes through this tiny private wormhole, a direct, hidden geometric link between them. The implications of this conjecture are profound, especially for our understanding of the nature of spacetime. Geometry, the very stage of the cosmos, could be woven from quantum connections. Physics faces a monumental challenge. It rests upon two incredibly successful pillars. General relativity describes the universe on large scales, planets, stars, galaxies, the expansion of the cosmos. Quantum mechanics describes the universe on small scales, atoms, electrons, photons, the fundamental forces. But these two theories don't quite agree. Unifying them into a single theory of quantum gravity is a major goal. The EPR conjecture could be a vital clue in this quest. It offers a potential bridge between these two domains. Wormholes, or ER, are a concept born from general relativity. Entanglement, or EPR, is a purely quantum mechanical phenomenon, a hallmark of the subatomic world. The conjecture directly links these two distinct realms. It suggests a deep, underlying unity. Albert Einstein was a true revolutionary in physics. His insights reshaped our view of reality. Yet he famously resisted some of his own theory's implications and the strange nature of quantum mechanics. Entanglement, with its spooky action, seemed too bizarre. Wormholes appeared to be mere mathematical games. He sought a more classical, deterministic universe, one that was locally real, predictable, and complete. The irony here is truly magnificent and profound. His own groundbreaking theories contained the very seeds of these stranger, more unsettling concepts. His theory of general relativity gave us wormholes. His insightful critique of quantum theory sharpened the scientific focus on entanglement. If the EPR conjecture proves to be correct, it would represent a stunning unification, connecting his gravitational insights about the large-scale structure of the cosmos with the quantum world he found so perplexing. The journey into the unknown is far from over.